So these sort of candy-colored points actually represent the locations of the galaxies. Now, the Milky Way, as I said, contains hundreds of billions of stars, and some of these galaxies are a little bit smaller, but some are actually even bigger. Some of the largest galaxies may contain as many as 1 trillion stars. So now if we kind of pull far enough away, actually, what we can see here, this is kind of our local group of galaxies. It's about 40 or 50 some odd galaxies. And we're kind of in the intergalactic boondocks. I mean, this is not a really packed part of the universe. So if you look at, let me see if I can pull back far enough to see. What I'm looking for is the Virgo cluster. Which is right here, this collection of red points that's kind of whizzing by. Let me actually put the brakes on a little bit. So the Virgo cluster is sort of our downtown area relative to the sort of suburbs here of our local group. So the Virgo cluster up here is packed with about 1,000 galaxies. The galaxy at the center of the sort of gravitational mosh pit at the center of the Virgo cluster is the galaxy M87, which is one of those stars, one of those galaxies that contains about 1 trillion stars. But the thing to notice at this point is that the galaxies are not sort of uniformly distributed through space. Instead, they're sort of clumped together. There are clusters, and then there are regions where there aren't many galaxies at all. This is a discovery that was made initially about 30 years ago. And it speaks to really the origin and development of our universe. And what we're showing right now are about 30,000 points. Each one of these represents the location of a galaxy. It's not the easiest thing in the world to determine the distance to a galaxy. So this represents the work of dozens of astronomers working over a period of decades to make these observations. And it was the astronomer Brent Tully who went through, collected all this data into one place, sort of one three-dimensional page on an astronomical atlas, and created this database, and then color-coded things by their associations to make it easier to sort of see what's going on. But this was the state of the art maybe 10 years ago. Now we actually have a process by which we're rapidly cataloging and measuring the distance to hundreds of thousands of stars. I'm sorry, hundreds of thousands of galaxies in the universe. So the image you see here now, the kind of bright yellow and aqua-colored points, are two separate surveys of other galaxies and their distances. The aqua-colored points come from the Sloan Digital Sky Survey. The yellow points come from the 2DF survey, the 2-degree field survey. So to give you a sense of what's going on, let me actually, I'm going to tweak this off here a little bit. I'm going to dive back down to our location in the center of this and look at the 2DF galaxies, because I want to underscore exactly what's going on here. When we so you'll notice we're pretty close to get close enough to the Milky Way to see what's going on. So here we're close enough we may as well be at Earth. We're so close to the Milky Way, even though we're maybe 1 million light years from home. And let me just move this around. So you'll see now, here is the 2-degree field survey as seen from Earth. So what we're doing is, each one of these circles represents the view of a telescope of that part of the sky. The telescope is looking at different parts of the sky, figuring out where the galaxies are, and then this actually corresponds to a physical plate that's attached to the telescope. We drill a hole for the location of each galaxy, attach a fiber optic cable to it, and then collect light to measure the redshift of the galaxy, which gives you its speed, which is an initial sort of first pass at estimating the distance to the galaxy. So this is a non-trivial effort, but it underscores sort of the amount of work that's required to do this. So this is how we're getting literally hundreds of thousands of galaxy locations now by this automated process of finding galaxies, creating specialized observations to figure out their distances, and then using that to create our three-dimensional map. Let's go ahead and pull back. So now you can see as we pull away, those individual views on the universe turn into sort of these, it's like taking a core sample down into the Earth. We're looking out into space and back into time. And as we look, as we look out into space and back into time, we're able to piece together now. You can see that the clumping and clustering of galaxies continues not just close to home but far away. And it's not obvious from what we just saw, it's not that there are no galaxies on the lower right-hand side or on the upper left-hand side. It's just that we haven't looked at that part of the sky. So the reason we see this sort of bow tie shape to the universe isn't really shaped like a bow tie. Instead, it's just that that's the part of the universe where we've actually made the observations to determine the distances to these other galaxies. So we're now maybe about 1 billion light years from home. And here we really have to confront the issue that I mentioned early on. The points that I just added are actually not galaxy locations. Now we're highlighting the locations of quasars. These are the bright cores of young energetic galaxies that we actually don't see nearby. We only see them billions of light years away. And what that really means is we see them billions of years back in time. So now what we're confronting is the idea that as we look out into space and look back into time, because we use light to make our measurements, we're seeing the universe as it was. And quasars seem to be something that took place earlier in the history of the universe. They're not common now, but they were common billions of years ago, earlier in an earlier epoch of the history of the universe. And to just underscore that point even further, as we pull back farther yet, let me go ahead and brighten what I'm using here as the background image. I just want to make this, inevitably what's going to happen is it's going to become sort of completely psychedelic. But I've just added this sort of brilliantly colored backdrop to all of this, is the cosmic microwave background. Now this completely surrounds us. It really is evident when you see this in a planetarium because it fills your field of view. Every direction you look, you see the cosmic microwave background. This mottled appearance of the cosmic microwave background is due to tiny fluctuations early in the history of the universe. This really corresponds to a baby picture of the universe. So long before galaxies had formed, in fact, just as matter was and atoms were forming, is when this image dates to in the history of our universe. So the universe is about 13.7 billion years old. The cosmic microwave background dates to a time about 370,000 years after the Big Bang. So this baby picture represents, if you look at the sort of bright red areas, correspond to the densest, hottest parts of the cosmic microwave background. The sort of dark black to blue regions correspond to the sort of less dense, not so hot parts of the background. Now, these fluctuations from hot to cool are only 1 part in 100,000. So it's like we've really cranked up the contrast on this image. The variation is tiny. And yet this variation in density and temperature was enough to create the structures that we see nearby, the clusters and superclusters, actually, of galaxies that we see in the structure of the nearby universe. So one of the things that cosmologists have been working on, including on supercomputers about half a mile from here, is modeling the physics that takes us from this cosmic microwave background, this tiny fluctuation of 1 part in 100,000, to the densities and structures that we see today. And dark matter is actually critical to achieving the densities required to form galaxies, to form stars, and in fact to have life in the universe. So there's mysterious dark matter that we're still trying to puzzle out the nature of. It's actually a necessary ingredient of the universe if you want to form life.